Let's get down to some real business then. So last time was a bit of an overview, but this time around I want to get down to some real sort of, detailed stuff. So at least for most of today, it's going to be all fairly simple things, matter of terminology here. I would like to talk about languages. This is something I didn't really say anything about. I didn't try to say anything about languages last time, but you may have noticed the title of our textbook is Formal Language, which if you tell that to an ordinary person, it's not what they think it means. Formal language. Most of what we call the theory of computation, or what this class is all about, it can be phrased in terms of machines, and that was what I was mostly talking about last time. But all these things about machines can be equivalently phrased in terms of what we call languages. And I don't mean ordinary languages like you usually think of the word, but there's a technical term, and these are called formal languages. So let's talk about languages. At first, this will seem to have nothing to do with anything that I was saying last time or anything about computation at all, but we'll get there eventually. So, very basic terminology here. This is obviously inspired by the ordinary word language. Anyway, here's first bit of basic terminology. An alphabet is just a set, it should be finite, set of symbols, and a language is built out of an alphabet in this sort of formal language theory. Like, for example, A, B to Z. Most of the abstract examples that we're going to be talking about use something like this as the alphabet: A's, B's, and C's. All right, or you could use as an alphabet, say 0 and 1. This would be like a binary alphabet, which you probably know that on some level all computer data is based on this alphabet. You never actually do this, but you could in theory take all of the information in a typical computer and express it in terms of just zeros and ones. Or something like more common computer alphabets that you may have heard of: the ASCII alphabet or the Unicode alphabet. ASCII was kind of old school. I believe there are 128 characters in the standard ASCII set, which includes all lowercase, uppercase, Latin style letters plus numbers and some other ordinary stuff on the keyboard. Unicode is like a more modern, expanded version of that, which includes symbols from other languages and other alphabets, and so on. All right, anyway, you could choose any of these things to count as your alphabet that you want to work with. The alphabet is usually denoted by a capital sigma. I don't know why, but this is what they usually, whatever the alphabet you're talking about is, they usually write it with this capital sigma. And it is a set, right? Okay, another bit of simple terminology that I think you're all familiar with. A string is what you think it is, if you know what a string is in programming. A string is just like a sort of a word or something that you make by putting together letters from the alphabet. So I would say it this way: a string is a finite, strings are not allowed to go on forever, a finite sequence of alphabet symbols. All right. So, for example, if my alphabet is just, say, 0, 1, then strings look like, 0, 0, 1, 1, 0, 1. That's a string, and so on. 1, 0, 0, 1. Just 1 by itself, that would count as a string of a single alphabet symbol. All right, these are all strings, and I hope none of this is too surprising to anyone. Strings have a length, which we are often going to discuss, and in our book, the length of a string is written with sort of like absolute value signs. So that is the length of that string, and the length of this string is 4, because there's 4 alphabet symbols in that string. Every string has a length. All right. There is a everybody's sort of favorite string, or a very special string that comes up often, although it's not terribly useful all by itself, is any alphabet can make the empty string. And this is just a string consisting of no characters. And it's kind of stupid and isn't really used for anything, but you end up talking about the empty string a lot, just like the number 0 is kind of stupid, but it's useful for talking about things. So any alphabet can make the empty string. Unfortunately, the empty string is a little hard to write down if you're writing strings like this. You know, writing the empty string in a programming language is usually just like quotes with nothing inside. In this class and in our textbook, the empty string is always going to be written with, this is the epsilon, the Greek letter epsilon. All right, so when you see epsilon, that is the empty string. Even though it looks like one thing, it's not, like the epsilon is not a letter from the alphabet. The epsilon is, you could say, like a variable which represents the empty string. All right. So I will just reiterate, this is not in the alphabet. It represents the empty string. So the length, for example, of the empty string is 0. Even though, I mean, you see one thing there, but that epsilon represents the empty string. So its length is 0. And it is the only string of length 0. All right. Typically, just when we're talking about stuff, usually as far as like variables and whatever, we use things like A, B, C, etc. for alphabet symbols. Typically, if I write something like X, Y, Z, these would usually represent strings. This is not a rule, but that's just usually how we're going to write down our variables. All right. There is one important operation that you can do on 2 strings, and that is to just sort of like write them one after another. So if I have, let's say X is A, B, A, B, and Y is B, A, B, then we can stick them together. And the way that we write down that operation is, actually we don't really use any kind of symbol for it. Then we just write like XY would be X, so that's AB, followed immediately by Y, BAB, right? So there, like there's the X and there's the Y. This is called the concatenation of X and Y. All right, this is string concatenation. In Python, you would write X plus Y, and if X and Y are strings, that would stick the strings together in this way. All right, in our book, they just write X, Y. That's the concatenation of X, Y, and I will just say, generally speaking, X, Y is different from Y, X, right? If X, Y means you put X first and then Y. Y, X means you put Y first and then X, and usually those are not the same string. All right. It is always true, though, that X followed by the empty string, what is that? X. It is X, yeah. If you start with X and then add onto the end of it nothing, you still get X. So that's X. And this is also equal to empty string followed by X, right? This is the concatenation operation. I hope everything I'm saying is pretty straightforward. We just got to get so that we're on the same page here. One last operation that we have for strings, and it's really just a variation of the concatenation. When I write X squared, this means XX. So in this way, you can make powers of any string. So like X to the 4 means X, 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 right? no funny business here. So for example, if, I can just say it this way. So something like ABA to the third, this would be ABA, 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 right? This is powers of a string. This is something that we're going to be talking about fairly often, and there's not a lot to it. We define the 0 power is defined to be the empty string, because that's sort of the only thing that makes sense. If you want to talk about the 0 power of something, it means I have ABA and I want to repeat that 0 times. I guess that's the empty string, right? This is kind of in the same way that any number to the 0 power equals 1. And then we don't talk about negative powers of a string, because that doesn't really make any sense. A negative power you might think is some kind of inverse of a string or a reciprocal of a string, which that makes sense for numbers but not strings. So there is no such thing as, say, x to the -1 or anything like that. 0 you can say is the empty string, but negative powers, you can't really say nothing. All right, this is alphabets, strings, and now I can tell you what a language is. A language is just a set of strings on some alphabet. A language is just any set of strings which use the same alphabet. All right. There is obviously some kind of analogy between this type of alphabet and language versus like ordinary, like real life human being alphabets and languages, and I'll say something about that in a moment. All right, but anyway, that's what a language is for our purposes. So, for example, for, let's say, the alphabet of 0 and 1, here's an example of a language. 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. That's a language. This is a language. All right? If I were to describe this in words, I would say this is the language of all strings of length 1 or 2 on this alphabet. All right? That's a language. Or something like, we are often going to use fancy set theory. I mean, not too fancy, but as far as writing sets like this. So this means 1, 0, 1 to the power n, where n is any natural number. So that fancy looking capital N there, so this is a language. And in our class, this means the natural numbers starting at 0. There's some controversy in mathematics at large about whether you should start the natural numbers with 0 or 1, but in our book they always start with 0. All right? So this right here is a language. It consists of, when you use the n equals 0, that's the empty string. When you use the n equals 1, it's 1, 0, 1. But you also include when the n is 2 or 3 or whatever, and you get any set of strings. That's all that language means. All right? One more example. Sorry. That means the empty set. That's also a language. This is kind of a stupid language, or like it's not really useful for anything, but again, it is something that you want to talk about every so often. The empty language, all right? Language just means set. That's really what it means. Set of strings on a particular alphabet, all right? The empty language, that's kind of the smallest possible language you can make if you start with a certain alphabet. There's also, it is also useful to talk about the biggest possible language you could make, and that would be just the set of all possible strings. And there's a notation for that too. I'll write this as a little definition here. It is written that way. That's a star. It's kind of ugly looking star. Sigma star. This is the language of all strings on sigma. I'd say strings on sigma. I mean strings that you can make out of alphabet letters coming from the alphabet sigma. So when we write the star, that means all possible strings from this particular alphabet. All right, and there's a name for this. This star is called the Kleene closure. This guy's name, most people say Kleene. I think that's not actually, I think it was a Dutch guy and it was pronounced somehow differently from that, but pretty much everybody that I've ever heard talk about him says Kleene. I think it's more like Kleene or something like that, but I'm going to say Kleene, or, well, more often I'll just say star. But anyway, this is just the set of all possible strings that you can make using that alphabet. And this set is always infinite. Like some of these languages that I've discussed have been finite, like that one right here only has 6 different things in it. But this one here is infinite because it has every exponent, where that exponent could be any natural number. And this one right here is always going to be infinite if you consider all possible strings. So this is, sigma star is always infinite. When the sigma is non-empty. And we don't really talk about an empty alphabet is not really something that is ever going to come up. All right, this is very basic terminology. I hope that there's, nothing fancy here, not yet at least. Let's talk very briefly about kind of an analogy to what most people, ordinary people, when they talk about language, like a spoken language or a written language. Maybe I'll call this a written language instead. A written language, like a human language, has, this could be a human language or even a programming language, has an alphabet somehow, right? Of actual symbols, and what you call the language, you could think of, it's a little tricky if you try to define exactly what the language is, like the English language. What is that? Everybody kind of knows what it is, but to say specifically what it is, I'm going to say, I'm not a linguist, I'm just going to say, like by way of analogy, the language consists of strings which actually make sense in English. So I will say it this way, consists of all allowable, that is to say like grammatically correct sentences that you can possibly say. Or write, I guess I'm talking about writing, all right? So for example, if you want to model the English language based on the terminology that I've been using, so for example, I would say to get the English language, it's like somehow like the English language, the alphabet that you use consists of A, B, C, down to Z. Let's ignore capital letters just because I'm trying to make everything simple. And then the English language, you need, let's also ignore punctuation, but you do need like the space character to make an English sentence. It's important to separate the words out. So I'm going to say something. Can I just sort of write it like that? I don't mean the underscore. I just mean a space. You need a space to go in between words if you want to make valid English language sentences. So it's like that's the alphabet, and then the language is, I could call it something, maybe I'll call it sort of a big old fancy E. This is the English language. So remember, the meaning of the word language for us is the language is a set of allowable strings, where allowable in this case means it's like an actual sentence in English. So for instance, the string like, I have a dog. This is an element of the set E. Where the set E is the set of all legal sentences in the English language. All right? So that is an element of E, but something like I howl a dog, this is not an element of the English language, because that doesn't make sense, because that howl is not a word. All right? Or something like I have, I'm going to say this also is not a legal English sentence, right? Etc. This is the analogy between formal language as we are talking about it and like real life languages that people speak. This is a very simplistic analogy, and it really doesn't hold up to much scrutiny. Like one thing that is a feature of human languages, natural languages as I call them, natural languages don't really obey strict grammar rules. Like in English, for example, you can try to describe grammatical rules, but it's not like people have to obey those rules. You know, like I can speak with slightly incorrect grammar and you will still understand what I'm talking about. And you would still recognize that, yeah, I'm speaking English, even if I say things in a weird way. All right. In this kind of formal language setting, we are trying to think about languages where there really are strict rules, and you cannot make statements that don't abide by the rules of the language. All right. This is like loosely true for real life languages, but not entirely. The analogy is much better suited to computer languages. So in computer language, like there really is such a thing as a sentence which is either right or wrong. And if it's wrong, it doesn't make any sense at all. And if it's right, then it does make sense. So in a computer language, the analogy is sort of more appropriate. The language would be defined as the set of all, I will say, syntactically valid programs. Syntactically valid means it makes sense in the programming language. Like you can try to run it and it won't give you an error. All right. I don't mean necessarily programs which do something useful, but just programs which are valid. All right. Not necessarily useful, but at least they are correct and they will actually do something, or maybe they'll do nothing, but they won't give you an error when you try and run it on your computer. All right. So, for example, from this point of view, if you ask me, like, what is Python, the computer language? From this point of view, I would say Python is a set of programs that you could possibly write which obey this and that rule. Like, there are certain rules for how you have to structure a Python program. And the set of all allowable programs, that is the language, right? From this point of view. This is, of course, a terrible way to describe what is Python. If an ordinary person asks you, what is Python? You would just say, it's a programming language. What do you want from me, right? But technically speaking, this is what we're talking about when I say a language, all right? And from this point of view, what is a compiler or an interpreter of one of these languages? Well, it's something which reads your program and actually tries to do something based on your instructions of the program. But one thing at least that it has to do just before trying anything is it's going to read the program and make sure that, for example, you're actually writing Python. Like the program has to make sense on some basic level. And what I want to talk about is sort of, this is going to be our first type of machine that we're going to talk about in this class. So we are, the general trajectory of this course is we are going to be talking about various abstract types of machines of increasing complexity, eventually working our way up to the universal machine, which was sort of invented by Turing. But we're going to start off talking about much simpler machines, that is, machines which can do a lot of stuff, but maybe they're not machines that can do anything. But our very first type of machine is still something that is like manifestly useful in the context that I've been talking about, and that is a machine which somehow reads a string one letter at a time. Of course, this is how a real computer works when it reads your code. We usually don't think of it in this way, but you know, a real computer does have to read your code one letter at a time. It somehow assembles things into meaningful chunks. But anyway, a machine which reads a string one letter at a time and tells if the string is accepted or rejected. So you could imagine this as like a very simple type of compiler, which it doesn't actually do the program, but at least it like reads through it and tells you, is this valid or not? That's all. That's all it does, all right? A machine which reads a string one letter at a time and tells if that string is accepted or rejected. All right, and this is called, so actually we're going to talk about a few different types of machines that have this basic framework, but we are going to talk about what we call, this is our first sort of big topic, the DFA, and this stands for deterministic finite automaton. Deterministic finite automaton. This is our first and the simplest of all the types of sort of computing machines that we're going to be talking about as we go throughout the semester. The simplest type of machine that we will talk about. So maybe we'll just try and say what these three words mean. Deterministic means basically no randomness in this machine. Another way of saying that is if you give the machine some input, it will always do the same thing with the same input. So if I say, the idea, remember, is you give a string to the machine and it tells you if the string is valid or not. And if you give it the same string twice, it's going to give you the same answer twice. That's what deterministic means. So no randomness, i.e. the machine's behavior, maybe I'll say the machine always does the same thing. When given the same input. There's no randomness in the way that it operates. All right, next is finite. This means, and this is what I will say, this will become a little clearer in a moment, but basically the machine has only finitely many states. And I'll say what I mean by that in a moment. Finitely many states. You could imagine the states represent something like the machine's memory or the different configurations that the machine could be in, something like that. This will become immediately clear once we do some specific examples. And then, automaton is just sort of a fancy word for robot or machine or something like that. This is the deterministic finite automaton. I am going to give us a simple example. So the DFA, remember the idea is we give a string to the DFA, we give it a string, and it either accepts or rejects the string based on some kind of rules, right? Some rules. And those rules are determined by states in a way which you will see real quick. So let's do, this is a very simple example of what I will call an even length machine. That is, I'm going to give a string to the machine, and it will accept if the length of the string is even, and it will reject if the length of the string is odd. That's all. So this is very simple. This is far less complicated than telling you if a Python program is valid or not. This is going to be an even length string, and using, again, I'm trying to make this as simple as possible, just this as the alphabet. So the only strings you're allowed to give it are A or AA or AAA, just strings only using A. And it will accept if it has an even amount of A's, and it will reject if it has an odd number of A's. That's the idea. All right. So let me just say input looks like something like, you know, AAAA or AA, etc., right? And we accept if it's even length, reject otherwise. Reject if it's odd. All right. Here's how we write down a DFA. We are going to write this using what we call this a state diagram. And it has, in this example, just because I know what I'm doing, it has two states and it has arrows on it. I'm just going to write it down, and then we can talk about what all of this means. All right. Those are two arrows, each of them labeled with an A. And the circle on the left is going to be kind of doubled up. All right. Once you know, real ones know how to look at that and realize what it is. So this is a DFA, which has a certain meaning, and actually this is a description of a machine which does exactly what I was trying to say about accepting if it's even and rejecting if it's odd. So what's the meaning of all of this? I will tell you. So first of all, the arrows, these arrows with an A, these are called the transitions. All right. The circles are called states. They are the states. I said deterministic finite automata. The finite means there are finitely many states. So a DFA cannot have infinitely many states in the diagram. All right. And then that circle with the sort of extra business going on, this is called an accepting state. And the other one is a rejecting state. And then the arrow, sort of that arrow pointing from nowhere onto that first state on the left there, that indicates the starting state. So this arrow here tells you where to start. The starting state. All right. And how does this diagram sort of describe a machine here? So to evaluate a string, you start in the starting state, which is the one on the left in this example. Start in the starting state. And you read your string one letter at a time, and as you read those letters, you kind of bounce back and forth in the diagram. So you follow the arrows one letter at a time as you read the arrows in your string. So you start in the starting state and then read your string. One letter at a time, left to right. And bounce around the arrows as you go. And then when you're done reading the string, you either end up in the accepting state or you end up in the rejecting state. And that determines if the string should be accepted or rejected. All right? You read your string left to right, you bounce around the arrows as you go, and where you end determines sort of accept versus reject. It says reject. Right? So in this particular example, if you end up on the left, it should be accepted, and if you end up on the right, it should be rejected. All right. So let's see if that DFA right up there, does that actually do sort of as advertised, except if it's even and reject if it's odd. We should just sort of test some out. So let's test out something like AAA. That is odd, so it ought to be rejected. And you can sort of do this with your finger if you want. You start over here, you go A, and you end up over here. That is in the rejecting state, and so this is rejected. This is rejected. All right, what about A? I go A, and now it's accepted. So it's accepted. And I think it shouldn't be too hard to convince yourself. This really is about evens versus odds, right? If you have an even amount, that means you go back and forth and you end up on the left. If you have an odd amount, you go back and forth, but you end up on the right. So this is accepted, etc., right? It really does do what I said it should do. Is that making any sense to everybody? I hope so. Sometimes when you make diagrams like this, it is helpful to and this is not like part of the diagram abstractly, but sometimes it's just helpful to label the states. I might label them as sort of, this is like the even and this is the odd, right? Meaning that this is the one you'll end up with when the strings are even length, and this is the one you'll end up with when the strings are odd length. So sometimes it's helpful to kind of try and keep track. These are like comments that you would write in code. These labels don't have any meaning per se, but they are helpful for me to understand what's going on in the diagram. All right. What about, anybody want to say, the empty string here, is that accepted or rejected? I didn't really say what to do with the empty string, but what do you think?
Would it be accepted because you just start in the accepting?
Yeah. You start here, and then if I tell you, like, okay, now do the empty string, that's like, do nothing, okay, and then I end up here, I guess. So it would be accepted. That's how you handle the empty string. In this example, empty string is accepted, but that's supposed to say accepted, sorry. I actually feel good about that because the length of the empty string is 0, and 0 is an even number, and so it ought to be accepted in this example. Since this is supposed to be accepting any even lengths, the empty string does count as an even length. All right? Great. This is sort of baby's first DFA. And, a lot of what we're going to do for the next little bit, like your homework assignment, will consist of a bunch of, like, here's a description of something, you make me a DFA that does that. Or the other way around, I could say, like, I show you a DFA and then tell me in words what this thing is supposed to be doing, right? That's the idea. Let's try, we got 10 minutes or so? Yeah, let's try a couple more examples. Any questions about this before we do some more examples? I think, you will, like I said, as we go along, begin to be able to just sort of like at a glance have some idea of what this represents. And this is like, it's kind of like learning a programming language. Like you have to, there's a bit of a process and it'll take some time a little bit to learn to kind of think in this mindset. You have to learn to sort of think like the machine thinks. Anyway, let's try another example. I got 2 more. I have some for you to try, but maybe we'll have to wait till next time for that. How about on the alphabet? So this is going to be more interesting. A's and B's. So this time the diagram will have some arrows with A's on them, but also some arrows with B's on them, because it has to tell you, like, from here, where do you go if you see an A versus where do you go if you see a B? Anyway, I want a DFA which accepts any string with no B. All right? It accepts a string with no B's. If there is a B, it should be rejected. That's the idea. If there is a B, it should be rejected. It accepts only strings with no B. Now, this one also I can do using 2 states. For more complicated rules, you're going to have to use lots of states. But this one, just because we're getting started here, I happen to know that this can be done with only 2 states. The idea that I have in my mind when I'm designing this DFA is, as soon as you see a B, there might be more stuff after that, but if I ever see a B, it's going to be rejected. I don't care what comes after the B, right? And so what I'm going to do here, I have basically two states, and the way that I'm going to think of these states is sort of the starting state is kind of the no B's. Because when you begin, there's no B's, right? Because you're starting with nothing. You think of the starting state as representing where you begin with the empty string. There will be no B's. But if I ever see a B, it's all over, right? Then it should be rejected. So this one is going to be accepting, because that's when I want, if I have a string with no B's in it, that should be accepted. The other string would be, yes, B's. There are some B's, or maybe just one B or whatever, but that should be a rejecting state, because I do not want to accept any strings that have B's in them. And now it's just a matter of where should I put the arrows, all right? So let's think about if I begin and I begin over here. I'm thinking about, I have so far looked at a string which has no B's in it, and then I see an A. Does that mean the string, I'm talking about the arrow, should the arrow go across here with the A, or should the arrow just loop back here? That is allowed, by the way. You can have an arrow which either goes to the other state or just goes back to itself. So the question is, if I have a string with no B's, and then I read the next letter and it's an A, should I go across or stay here? What do you think? Yeah? I think stay here. That's because if there were no B's and the next letter I read is an A, then I guess there's still no B's, right? So I'm going to put one of these. If you've not seen any B's yet, and the next letter you see is an A, then you still have no B's. All right, but if I'm in the no B state and I see a B, well then, that's a B, so I go across to the other state. There are some B's now, all right? And now we need, I haven't told you exactly what counts as a DFA, but this is not good enough for my final answer. In a DFA, you need arrows from every state, because I haven't told you like what happens if you're over here and you see an A or a B. So let's talk about from this state, where's the arrow with an A? If you have already seen some B's in the string and the next one you see is an A, should we stay over here or go back to the other side? What do you think? Yeah? Stay over there, yeah. If I've already seen some B's and the next letter is an A, it still counts as a string which already has some B's in it. So I'm going to put this arrow with the A. And then similarly, from the state on the right, where should the B arrow go? Should it go back across to the left or stay on the right? What do you think? Yeah, it should stay on the right. Yeah, if I've already seen some B's in my string and I see yet another B, it should just stay over here. Now the way that you can write another loop here, but this is typically written like that. A comma B on one arrow there. You can write two loops, but you will look awkward in the club if you do that. Write the comma. That's what they like. They will let you into the club. All right? Yes?
Do you have to write the A's and the AB at all? Because couldn't you just do the transitional one from the accepting to the rejecting with just B?
And then don't write these?
Yeah.
So it is, I haven't told you exactly what the rules are, but it is a rule for all DFAs. They must include arrows from every state, which are labeled with every letter. The reason is because, so after doing this, you should probably try and like check your answer. For example, is AAA accepted? Get your finger out. You start here, and I go A. So it finishes here, and so it is accepted. So accepted. Or AB, this would be starting here. AB, that's rejected, right? Rejected. Or something like ABAAB. This is why you need those arrows on the right side. You would start here. I go A, B, A, B. Now, if you didn't have these arrows here, you would just kind of get stuck. But so this is part of the rules about when you make a DFA, you're not supposed to ever get stuck like that. You want to be able to at least read through the whole string and end in a rejecting state. So in order to process this whole string, you need to go A, B, A, B. So you need these looped arrows. Anyway, that is also rejected. All right? And I feel like this is working the way I want it to. What about the empty string? The empty string will be accepted in this case. Is that valid? I think that does obey the instructions here, because the empty string has no B, and so it should be accepted. Right? Great. Let's do one more. And then next time, I'll have some opportunity for you to try some. So here is a fancier one. A DFA on this alphabet AB. Most of our examples actually are going to use AB. If you look at some textbooks, they use 0, 1 all the time, because that's more like more awesome hacker style binary, but our book uses A's and B's. A and B, and I want to say accepts, this is a little more complicated, any string. This is actually some kind of combination of the two examples that we just did. Any string with an even number of A's and no B's. An even number of A's and no B's. So the first example we did was just the even number of A's thing, and the second example we did was no B's thing. This is both of them. Unfortunately, there is not really a very straightforward way to, you might think, can I just somehow like chain together these two examples? The answer is not really. I mean, there's some things like that we are going to talk about, but it's nothing so simple that you can just sort of stick them together in an obvious way. An even number of A's and no B's. All right? Now, like I said, you're going to have to get used to thinking about thinking about this kind of a thing and then translating that into a DFA diagram. But when I see this, first of all, I see this even number of A's. This makes me think of two states that it has to go back and forth between. Whenever you see something about evens or odds, you are always going to think of that in terms of you're going to have two states where it goes back and forth, even versus odd. The no B's, so here I have this kind of like two states, sort of like this. This is in the back of my mind. Whenever I see even number or odd number or whatever, I think of two states that go back and forth. And then the no B's thing, this is like what I had before. This part I think of as somehow one of these. This you could say, maybe you've been there. I would call this like a permanent rejection kind of situation. You've been there? I've been there. This is like, as soon as you see a B, it's going to be rejected no matter what happens after that, right? So I want some kind of a combination of these two situations going on. My DFA is going to have basically two states that keep track of even versus odd A's. But then at any point, if you see a B, it's going to go to this kind of permanent rejection kind of state. So what I would come up with is something, I'll just have to tell you the answer because we got to go in a moment. I'm going to make something like this. This gets me that even odd thing. But then, like I said, if you ever see a B, it should go to one of these like permanent failure states. So I'm going to put this one down here. I will just call this one fail. And I'm going to put B arrows going there, right? So if you ever see a B, it goes to the failure. If you never see B's, then you get to kind of go back and forth between these A things. Now, I need more arrows, and I also need to tell you which of the states should be accepting. Can anyone say which one of those should be accepting? It's not the one on the bottom, because that we want to always reject. What about the two on top? Yeah? The one on the left, actually, yeah, you actually don't know until I tell you. I want to start on that one. So that should be the starting state. That should be the accepting one. As far as the evens versus odds, that's going to be the one which catches all the strings which are even length. Great. And then we also need more arrows. So in a DFA, every state must have two outgoing arrows, one A and one B. So I have enough arrows here. I also have enough arrows here because there's the A and there's the B, right? But down here, I need an outgoing arrow for an A and an outgoing arrow for a B. Can anybody say where should they go? I kind of have already said that. Yeah? Yeah, they should both loop back to this state because this is meant to be sort of a permanent failure state, which is inescapable. All right, that's it. This is our answer. This is what we're going to be doing problems like this for the next couple times, and variations on such. All right.